Hello, everyone. Today, I have the pleasure of introducing Irene Donata and Antonino Ingargiola.
Right.
So with a PhD in mathematics, Irene is a data scientist at Agile Lab, and with a PhD in IT and an ex-co-founder, Antonino is the lead AI architect at Agile Lab. Today, they will talk about building scalable video search systems. So let's please give them a warm welcome.
Thank you, everybody, for coming to this presentation. Today, we will talk about this research project that we built in the past months at Agile Lab. So let's start just with one word for the team. This has been a collaboration between some of us in Agile Lab, data scientists, AI engineers, and some folks in academia, Fabrizio Silvestri at University La Sapienza, and Diego Reforgiato at University of Calabria, and his student Rashid Maidan, University of Calabria. So why this project started? So we thought about a challenge we have nowadays. In many contexts, we produce tons of videos. Every day, we produce millions of videos. Every hour, there are videos get uploaded to different platforms. But it's not easy to search inside these videos semantically. Like with large corpuses of text, this is kind of easier. You can do keyword search, you can do vector search. But with videos, this is more challenging because the volume is just so huge that you cannot do that, just the naive thought of embedding the whole video and then searching it, assuming that there is this model capable of directly embedding the video content. So we set on our goal to build a system that will enable semantic search on large archives of video. With these two requirements, one, that it should be extremely efficient computationally, and it should be multimodal as a search interaction. So you should be able to search writing text, description of what you want, or images as a reference. And this could have several applications. For example, broadcasting companies that need to search into their archive, or investigative analysis. And so with this in mind, we kind of need a cool name for the project. And we settled with Deckard, reference on an old movie that we loved. So the application, this is kind of the front end of the application that allows to browse an archive of videos, select some object or query with some text what you need, and allows to get the result. But beyond the front end, how did we build the system inside? So I give the mic to Irene that can explain the whole system.
OK, this is a very high-level design of the Deckard pipeline. We divide it in 4 main steps. The first 2 are preprocessing steps performed on batch and offline. And they serve to store all the entities that we care about. So, for example, people, their faces, vehicles, and so on, and embed them so that we can quickly retrieve them at the first step using from a database. And the last step is performed on demand. Once that we have retrieved the video fragment of those entities, we can ask an AI agent to help us with the analysis of the video and to watch this video for us. So first step, detect and track. We need to identify all those entities and track them along the video. But before, we need to load the frames of the video. So a video is a long, contain 1 hour video contains 100,000 frames. So it depends on the quality of the video. It can contain more or it can contain less. But anyway, we don't need all those information. We can subsample these frames without losing meaningful information. And so we decide to go for 1 frame out of 4. The number of how much you downsampling, it depends on the video quality. So better to check. Then we need to do object detection and tracking. It's important to select a model that is light enough, because as we see, we have many frames. So, but we still need accuracy. So we decide to use YOLO 11 from Multilytics, that is known to have a good accuracy, still maintaining a good speed. And we also use Bosort for tracking. That is another well-known algorithm for tracking. Our advice is to deploy this kind of model using a tool for optimize your hardware. So we use TensorRT. And also you need to do some test on the batch size. So for example, you can see from this, so as you can see here, we have an U shape of the throughput measured as a frame per second against batch size. So we need to find the optimal batch size for our hardware and our model. Now we have found all the entities, and we can have a billion. We can still have a billion of crops, and they can be very similar one another. If we have one video with a fixed object, the crops will be equal. We will have many duplicated crops. If we have a person that is moving, we can lose some of those crops because it doesn't change too much. So it's important to select the key frames, not taking all of them. So first we decide to filter the crops that are on the boundary and the ones that have low confidence. And then you can use a different method to select the keyframes. So, for example, you can look at the pose of the person, but we want our pipeline to be the lighter as possible. So we decide to use a simple heuristic. We downsample the image by an 8x8 times 8 resolution. So we obtain an hash of the image. And we compare all the frames using Hamming distance. So this is like looking the image from far away. If they look similar, we can discard duplicated. The second step is embedding. Here we have 2 requirements. One is that our crops need to be retrieved both by query by text and querying by images. So we need a B-model embedding. And second, we really need to be good at identification people. People may be dressed up, so we really need to understand if a person is the same person even if he has changed his clothes. So better to look also its face. And for the faces, we have some algorithms that are specifically trained to be good to recognize faces, like state-of-the-art is ArcFace. So we use ArcFace for the faces. Whereas for the other object and person, we use SIGLIP2, that is a multi-modal model. It has been released on February of this year, so very new model, and is an upgrade of the famous clip that perform a unique embedding, a unique space where you put both images and text. And okay, SIGLIP2 was very good. Was already very good, but we want it to be even better to recognize persons. So we decide to fine-tuning it with data that we have found online. And as you can see here, we have the table showing us the performance of SIGLIP2 base of the state-of-the-art on the benchmark Mars. And lastly, the performance after the fine-tuning. And we surpasses the state-of-the-art for identification after the fine-tuning. And mostly we are very good with the last metric that we reported that take into account if you the earlier you see the match, the higher is the score, so it's the more relevant metric, and we are very good at this one. And here just a 2D projection done with principal components analysis of some images embedded with SIGLIP2, and we can see the women are clustered on the left, whereas men are clustered on the right. So it works very well. And then we need to store all our data. We store, for people, we store a double embedder, as I say, so we have 2 vectors, and we store all the metadata that will allow us to retrieve the video sources. And of course, where do we store this? We store it in a vector database, and we decide to store it in a Quadrant, because it's an open source model that allow also for multi-index retrieval. And so here we are, we can query our Quadrant, but how do we query Quadrant when we have a double embeddings? So as we do for people. So we decide that first we retrieve the first thousands match using SIGLIP2 vectors, and then we rank the retrieval items using the face embeddings. And okay, once we have retrieved the items, we can see the metadata and retrieve the fragment. So we can retrieve all those videos where our crops were taken from. And we can ask an agent to watch the video for us, and then we can ask questions to the agent. This part is performed on demand, and this is the heavier part. So it will take some minutes. So because the agents need to watch the videos before helping us. It is built with QN 3.8 as his reasoning, as his brain. QN 3.8 billion is a reasoning model, and so he helps with planning. And he has many tools. He can decide which tool to use. And for example, he has a tool that is done with QN 2.5, that is a visual large language model. And so it's like the eyes of the agent. And he has other many tools, but I will not go too much into the detail of the agent, and I'll be glad to answer your question later if you want. And I hand it to Antonino.
OK, thank you, Irene. So we have seen a bit of the whole pipeline built, part is batch, part is real time. Now, I would like to show you some things that we did to optimize it and make it more efficient. Let's start with an example. First thing, we need to decode the videos. Videos are normally encoded in MP4 with the MP4 codecs. So what we can do, we can use FFmpeg, a famous and very efficient software to decode this video, and you see it on the left. You can use in Python PyAV, that is a wrapper for libav, that is the library underneath FFmpeg, and decode this video on the CPU. Then you get the frames. And if you want to do some model inference with these frames, you need to do you need to convert it from NumPy to PyTorch. So we have this torch from, oh, sorry. No, I'm kind of spoiling all the other slides. So you need to do torch from NumPy and copy the array into torch. Then you need to move it to the GPU, and you copy it again to the GPU, and it's very inefficient. Or you can use the GPU to do the video decoding, because GPU were born initially for this task. They have hardware units to do MPEG for decoding. With an NVIDIA, you can use this library, PyNV video codec, to actually perform this decoding on the GPU directly, very easily. You get the frames now decoded as kind of tensors in memory. You need to pass it to PyTorch. And one trick is doing zero copy. And there is a nice package called DLPack that is an open source implementation of a standard memory format for tensors, and allows to do exactly this. So instead of copying the array from the NVIDIA decoder to PyTorch, you pass the reference, and you don't need to copy. And this is much more efficient. OK, that's to give you some flavor looking at the code. So let's zoom out and see the whole pipeline. Initially, we had this kind of implementation in which we use the GPU only for model inference. So the most natural approach. We put the models on the GPU. We use the GPU for model inference. And all the rest of the processing was done on the CPU. So video decoding on CPU, the tracking of the frames, because once you detect the object, you need to link all these crops to understand this is the same object moving. So it's the tracking part. Then there is the keyframe selection Irene talked 1 minute ago. Then there is the embedding. We need to move back to the GPU. And then there is the storage. And this, now you know, we said it many times, is very, very slow. What we want to do, we want to do everything on the GPU. And this is actually the second version we built. As the first example, we can do it, the video decoding directly on GPU. And this is done with this PyNV video codec library. Because our target GPU is NVIDIA, so we use all the runtimes and libraries for this NVIDIA GPU, even though conceptually you can apply the same things to, I don't know, AMD GPUs, and will be a different tooling, but the concept will be the same. On top of the video decoding, we have some pre- and post-processing when we feed the data to the model and when we get the data out of the model. So there is always some kind of transformation that you need to do to these tensors. And we re-implemented all this transformation logic on PyTorch using CUDA. so the tensor stay on GPU, and everything is more efficient. Next, we implemented the algorithm inside the tracking and the keyframe selection, also on PyTorch and CUDA. So everything doesn't need to go to the CPU. And finally, with that trick that I talked before, the LPAC, we make sure that tensors are passed with 0 copy. So we avoid any copy as much as possible. Of course, if you need to create a new different version of a tensor, you need to allocate a new memory. Otherwise, if you just need to process the frame, you can pass a reference. With all these steps put together, we obtain a much more efficient pipeline with a roughly 10x improvement in the throughput. OK. So what lesson we learn implementing this? First of all, as we have seen, we have to run the inference of the model very efficiently. And the most efficient way to run inference on NVIDIA GPUs is converting it to TensorRT runtime. There are several other runtimes, but the most efficient for NVIDIA is TensorRT. It's the runtime built by NVIDIA itself. To use it, you need to convert your model to this format. And when you convert it, you need to specify like the shape of the input tensor and the output and so on. It happened, for example, for the YOLO model, that when you pass different resolution of images, for example, frames, the model was still working, but was very slow. So it's very important, we found that it's very important to pass the right resolution that we specified during the conversion to get the maximum performance. So if it runs, it doesn't mean that it runs at the maximum speed. That's the point. Second, the optimal batch size. When you do object detection, you can pass one frame, or you can pass a batch of frames that will be more efficient in principle. But how big this batch should be measured experimentally, because it depends on the video resolution. It depends on the size of the model. It depends on your GPU that you're using. So it's not something that you can come up with like with some back-on-the-envelope calculation. And that's another important point. The other point I want to make is avoiding CPU-GPU round trips. As everybody knows, this is very slow and inefficient. So instead, if you stay all the time on the GPU, it will be much smoother. And you will get much higher throughput. And finally, when possible, pass data, tensors with 0 copy. And luckily, we have this amazing project that is an open source project, the LPAC, I already mentioned it. It's kind of Arrow, Apache Arrow, if you know it, for table data. This is a similar project for tensor data. So they specify what memory format a tensor should have. They implemented a small C library on top of it, and an interoperability protocol. It already supports NumPy, PyTorch, TensorFlow, a bunch of frameworks. So it's really well adopted, easy to use, and I cannot suggest it more. And that's it. So to conclude, final takeaways. We set on this course to build a large-scale semantic search system for videos. And we demonstrated that actually this can be done Can be done if you don't embed all videos, but if you embed only entities that you are interested for. So you split, you divide the problem in detecting entities and embedding entities. And if you do it in an efficient way, this becomes manageable. So you should avoid these nasty round trips between the CPU and GPU back and forth because they kill performance. And what about the video VLM? VLM that supports video as input, like Qwen 2.5 or Gemini or several others. They are really, really powerful. But they are also heavy. They are unsuitable to be applied to such large-scale processing. So instead, they can be used on top to help with the retrieval and to help with the analysis of single individual videos once you found them. So OK for some specific ad hoc queries on narrow set of videos, not for large-scale application. And that's it. Hope you enjoy it, and you're welcome to ask any question.
Thank you, Irene and Antonino. Yeah, we can take questions now, and one of my colleagues will pass around the mic. Yeah. Wait, sorry, just a moment.
Yeah, thanks for your nice presentation. I was wondering, like, in this presentation, you shared the example of like face recognition. How generic is the application that you presented? Like, if you would make a video of this of your presentation, what would it retrieve then? Would it be able to retrieve settings or content, or is it only limited to face recognition and finding persons?
So I go? Or
OK, it's really good.
So basically, the system will find the entities that you set up to detect. So you can find people if you detected people during the preprocessing. You can find any object. YOLO has like 130 classes that can detect.
Okay, yeah.
So you can pick any of those classes, and then if you embed them, you can then search them.
Yes, okay, I understand.
Yeah, I will add also that instead of YOLO 11, you can also use YOLO E. There are new releases of YOLO that are open class, so they can perform a zero shot. So you can also add items that specific that you are interested. And then with the last part, the agent, you can, with this on-demand analysis, you can embed also the entire frame or little fragment of frame, and it will also keep the temporal dimension. So you can ask more specific question like, does a certain person went into the bulk?
Yeah, would it be suitable for fashion as well?
Absolutely. So we already are developing some application for retrieval dresses and also for demand forecasting using images.
Okay, thank you. Any questions? Yeah.
Thanks for sharing the amazing work. I had a question, like how many videos you had to use for the embedding part, not for the detection part, but for the embedding, how many videos were sufficient for you to get the right amount of embeddings so that agent can give the answer to you? And maybe an attached question is, how did you like evaluate the answer of the agent, if it is good enough in terms of searching and indexing stuff?
I have to say that we are still evolving the agent part. But of course, you need to evaluate the agent as a normal machine learning model. So you need to have a test set and evaluate as normal machine learning model.
Yeah, and as for the dataset question, right now we are using a few hundreds of hours of video, but we are interested in the throughput, because if we can keep the throughput high, then we can directly scale, adding more machines. And we know how to size, for example, the hardware to process an archive of millions of video in 1 month, whatever time you set to do the process.
Yes. Can we get the mic on this side? Yeah. Thanks. Yeah, you can go next.
Thank you very much. You are focusing on object. Yeah. How about action? Like, because videos contains a lot of action, and the key part of video is actually action is happening. So are you planning to do also on the action part? Yeah, basically, with this pipeline, you can add any model that you want in the preprocessing step. And then once you save it in your DB, you can retrieve it. For action, if you have a fixed set of action, you can save it directly as a metadata and then retrieve all the videos that have this action at that specific timestamp. You don't need maybe a full embedding of the action, but it's modular. You can add as many preprocessing steps that will enrich the metadata layer and then allow to search only on that dimensions.
Thank you. Yes, mic to the person in the second row.
I see a question there. Please wait a minute.
Yeah, I was wondering about the combination between the two embeddings, and you made this choice of first the object, then the face in the retrieval. I was just wondering, how did you make this choice, or did you see any way to kind of measure the effects of first retrieving the object and then using the face embedding, or did you consider kind of merging the two embeddings in some shared space, or yeah, what were the considerations?
Yeah, we thought about that. Maybe we could use, we have a joint embedding for text and images. Maybe we could have a joint embedding with also face, but it would have been more complex because there is no out-of-the-box model that does that. Instead, with SIGLIP2 is already, we just fine-tuned the model, but was already done. And also, we noticed that in most videos, you cannot see the face very well. So you cannot rely on it heavily. So first we, for example, find a general resemblance, like clothing of some person. And then if you can see the face, you use it just for re-ranking. And this is like in RAG, you first retrieve a lot of chunks, and then you use another model to do the ranking of the chunks to find the one that are more relevant to your question. It's a kind of a similar idea. And it turns out that it works really well and is easy to implement and quick to run. So.
Okay, thank you. So if I want to escape the system, I should switch my clothes?
Definitely. That's a secret.
Thank you. I think there's a person who's been waiting since a while.
Thank you. I was wondering about that throughput. Do you have any concrete numbers, like how much, what the throughput is on like a single 32 gig GPU, for example?
So I don't think we have the throughput number, but on the slides. But I can tell you, we use the A100 GPU as a baseline, and we try to maximize the throughput on that GPU. And we are on the order of 20x with respect to real time. So with a single A100 GPU, you could process 20 real-time full HD videos with average number of objects in it.
All right, thank you.
Okay, I think that would be the last question for now, and you can catch them later. But let's all thank them again.
Thank you.